This video is a supplement to the other video that introduced trigonometric substitution and should serve as how you would problem solve using trigonometric substitution in particular. So if you recall, when we do trig substitution, we find ourselves looking at something where we either substitute x equals a sine theta, x equals a tangent of theta, or x equals a secant of theta. And the reason we do this, we would do x equals a sine theta when we see something of the form a squared minus x squared. If we see something of the form a squared plus x squared, or x squared plus a squared, we would do the tangent. And if we see x squared minus a squared, we use the secant one. The reason we do this is because then we can use one of our Pythagorean identities to help simplify usually something that's under a square root. When we take the square root, it eliminates the squares. When we do this, there are things that we might see along the way. For example, we might see a trig integral, which is an integral composed of powers of trigonometric functions. We might also see antiderivatives that involve theta, just theta, not a trig function of theta, but theta or theta squared or something like that. And finally, we might see antiderivatives that involve other trig functions evaluated at theta. So as an example, if I have something like x equals a sine theta, when I find my antiderivative, it may involve the tangent of theta. And so the question then is, how can we write tangent of theta in terms of x, knowing that x is 2 times the sine of theta, as one particular example. So we'll look at all three of these types of scenarios. So our first example, we're going to evaluate the integral of x cubed over the square root of x squared plus 9. Because I see the square root of x squared plus 9, I know it's going to be a tangent substitution. We'll see why in just a moment. Now, because I've got the 9 there, I take the square root of 9 and get 3. So I use 3 tangent theta. Finding dx is always rather simple. We just substitute dx equals 3 sine squared theta d theta by taking the derivative of that. We now make our substitution. Okay, so integral of x cubed dx over that square root. Just putting things in exactly as they are. That's x cubed. Dx is all of this stuff. And then in the denominator we have the square root of x squared plus 9. Simplifying, we're going to cube the 3, which gives us 27, but then we multiply by 27 by 3, we get 81. We have the tangent cubed and still the secant squared. In the denominator I've got 9 tangent squared from the 3 tangent quantity squared. Now I'm going to factor out a 9 here, so I'll have the square root of 9. That leaves me with tangent squared of theta plus 1. Tangent squared of theta plus 1 is exactly the secant squared of theta, but when I take the secant squared of theta and find the square root of it, I just get the secant of theta. Now how did I get 27? I took 81 divided by the square root of 9, which is square root of 9 is 3. So I'll make one more simplification. Notice that I have secant squared, secant here. When I reduce, I just get the secant. Pulled the 27 out front. So now we have a trigonometric integral, like we promised could happen with these trig substitutions. This is where we left off, and now we have a problem of trig substitution, so a little embedded problem in here. I might try to save off a derivative of the tangent or save off a derivative of the secant. The derivative of the tangent of theta is secant squared of theta, and notice I only have the secant to the first power, so I don't think that's going to be the appropriate substitution. How about secant of theta? What's its derivative? It is the secant of theta times the tangent of theta. So for right now I've pulled that off, and I'm going to see if this works well. What's left? Well, what's left is the tangent of theta squared. I need to be able to write this in terms of the function whose derivative is tangent secant. So I need to be able to write tangent squared theta in terms of secant of theta, because the secant of theta's derivative is right here. Well, I can do that using my one of my favorite Pythagorean identities, that 1 plus the tangent squared of theta is equal to the secant squared of theta. So I solve for tangent squared by subtracting 1 from both sides, which is where this comes from. So now I can let u be equal to the secant of theta. So u is the secant of theta. Then du is the derivative of the secant of theta, which is the secant of theta times the tangent of theta. I've just got them reversed here. When we substitute, this is u, so it's u squared minus 1. Secant of theta, tangent of theta, d theta is all of this. So that just becomes your du. I'm going to keep the 27 on the outside. Antiderivative of u squared is 1/3 u cubed. The antiderivative of 1 is u. Now we substitute back in. And I have 9 secant cubed of theta minus 27 secant of theta. So now the trick is to figure out what is all of this in terms of x. And we need to remember what we started with. We started by letting x be equal to, it was 3 times the sine of theta. So I need to write this in terms of x. Well, I can do a little bit of work here. The sine of theta is equal to x over 3. Okay, that's good. And now if I think about this, I could look at a little triangle. It's supposed to be a right triangle. So down here is theta. Here is x. And the hypotenuse is 3. Sine is opposite over hypotenuse. Okay, so now I need to do a little bit of work. Kind of run out of room down here, but if I use the Pythagorean Theorem, this side becomes the square root of 9 minus x squared. What you'll find in these trigonometric integrals, or trig substitution problems, is that a quantity you see at the very outset of the problem will often appear towards the end. Okay, so we saw square root of 9 minus x squared. There it is again. So the question is, what about the secant? Well, a little bit of work here. I know that the secant of theta, no, I don't like the secant. Oh, I know that the cosine of theta, which is the reciprocal, is the adjacent over the hypotenuse. And so the secant of theta is the hypotenuse over the adjacent side. Okay, so the secant of theta is going to be the hypotenuse, which is 3, over the adjacent side, which is the square root of 9 minus x squared. Okay. So we said that the secant of theta was the adjacent, or the hypotenuse, which was 3 over the square root of 9 minus x squared. That was what we calculated before. And there we have 9 times the secant cubed minus 27 times the secant. Okay. So we could do a little simplification. We could cube this 3 in there, and then we could write x squared plus 9 to the 3/2 power if we wanted to, but we're not worried about that right now. We're just problem solving here. All right, for the next example, we want to evaluate the integral of 4 minus x squared. This was an example that I tried to have you do for class, and it did become a little bit overpowering. It was a little bit too much. All right, so I see this general form, 4 minus x squared, and so that I want to let x be 2 times the sine of theta. Why? Because it will then produce for us a simpler problem where we just have the cosine squared under the square root here. Derivative of 2 times the sine is 2 times the cosine of theta. I'll write it now. I should have written it before. Put a d theta there. When I go on to the next slide, it'll disappear, but keep it there in your head. We make our substitutions. So the square root of 4 minus x squared becomes, when I substitute, I'll do a little bit of extra work in the process. I'll square 2, which gives me this 4. I'll square the sine, which gives me sine squared. And dx becomes 2 cosine theta d theta. Again, remember that d theta should be there. Now I've got 4 in common with both of these terms. So I can pull the 4 out. I've left out a little step. I've pulled the 4 out. When you take the square root of 4, that's where this 2 comes from. Where'd this cosine come from? These guys back here are precisely from over here. So the question is, where did that extra cosine come from? And what we did, as I said before, we pulled out the 4. We've got square root of 1 minus sine squared of theta. But 1 minus sine squared is the cosine squared. Whoops. But it would be under the square root, and when I take the square root, that's where this extra cosine comes from. If I simplify, that is 4 times the cosine squared of theta. Now, this is another trigonometric integral. As I try to manipulate it so that I pull off a derivative, let's say of the cosine or the sine, I don't get even powers of trig functions, no matter what I do. And so we have to rely on one of our old friends, the half-angle identity, which says that if I take the cosine of, if I do the cosine squared of x, that is 1/2 times 1 plus the cosine of 2x. So that's what I'm going to do here. I'm going to take that cosine squared and write it like that. So I've got the 4 there. I didn't write it exactly that way, but there's the 1/2. I put it in the denominator. We will combine the 4 and this 2 here and find the antiderivative of 1 plus the cosine of 2 theta. So there's the 2 from the 4 over 2. Antiderivative of 1 is theta. Antiderivative of the cosine of 2 theta, let's think. The derivative of the sine of 2 theta is cosine of 2 theta times 2, so to compensate for that extra 2 I'd have to multiply by, I divide by the 2 there. Okay, so we go back to our little triangle business. X, we said, was 2 times the sine of theta, so the sine of x is, or sine of theta is x over 2. Let's draw our triangle again. So here's theta, sine is x over 2. If I use the Pythagorean Theorem, I would get 4 minus x squared down here. Okay, and lo and behold, that is exactly what we saw up here. There's that 4 minus x squared, just as I promised. Let's see, wait. I need another trig identity. Sine of 2 theta, sine of 2 theta is 2 times the sine of theta cosine theta. So I'm going to make that equivalence. So we've got 2 theta. I've just done a little distribution here. And, okay, so from this one, where did this inverse sine of x over 2 come from? I took this equation, solved it for x, or solved it for theta, which means we need to bring the sine to the other side. It appears as the inverse sine of x over 2. Over here is that sine of 2 theta equals 2 sine theta cosine theta business. Now we know what the sine of theta is. It's x over 2, and if you look at the triangle that we were, if you look at that triangle, it looks something like this. I ran out of, there's theta, there's x, there's 2, there's the square root of 4 minus x squared. So the cosine is square root of 4 minus x squared over 2, adjacent over hypotenuse. So there's 2, there's the sine of theta, there's the cosine of theta.